Good morning, everyone. Can you do me a favor and turn to page 1 of your unit handout that you were given yesterday? I don't know if you noticed, but the first lesson, that one-page lesson on the tangent function was actually page 0. That's because I rearranged my unit in this particular unit, and I didn't want to renumber everything because there's a lot of references to page numbers later on in the unit, so I just left that as page 0. Yesterday we looked at the tangent function as a graph. I'm not going to relive all of that right now, but you do need to know all of the features of y equals tangent of x, including the vertical asymptotes or non-permissible values, the x-intercepts, the y-intercept, the period, the domain and range, and any other features that are slipping my mind right now, but I think that's it. Today what we're going to do is finish off chapter 5 by connecting equations of trigonometric expressions to graphs of trigonometric functions. So we're going to be looking at solving trigonometric equations graphically, and then we're also going to be applying sine and cosine functions to real-world applications. So to begin with, we're going to do a bit of a review. This is really almost from the previous unit. It says solve the equation in example 1. The equation is 4 cosine squared of x minus 3 is equal to 0. And we have a domain of x can be any rotation angle from and including 0 up to and including 3. And we're asked to solve this equation two ways. So how do we solve it algebraically? I will remind you that this equation, 4 cosine squared of x minus 3 is equal to 0, is missing the linear term. Right? There's a quadratic term, and it's also missing an x, which I better put in there. It has a quadratic term because it has cosine of x quantity squared, which is what cosine squared of x means. And it also has a constant term of 3, but it doesn't have that linear term. This would be like me having an equation that would be 4a squared minus 3 equals 0 in Math 20 and saying, go ahead and solve that quadratic equation. There's no linear term. And when you solve a quadratic equation with no linear term, it's really just a matter of you rearranging the equation for the quantity you're trying to solve for. So if I add 3 to both sides and then divide both sides by 4, I get a squared equals 3/4. The next step, of course, would be to take the square root. Okay? But we're not interested in solving this equation. We're interested in solving this equation. So I'm going to do the same kind of thing here. I'm going to add 3 to both sides to get 4 times cosine squared of x is equal to 3. And then I get cosine squared of x is equal to 3 over 4. When I take the square root to get cosine of x, I end up with cosine of x is equal to plus or minus the square root of 3/4 or 3/4. You know, we've learned that at this level, this isn't a decimal kind of math. You don't plug things into your calculator to get decimals. We want exact values. So what we say to ourselves is that the square root of 3 can only be written as an exact value as the square root of 3. I mean, there's maybe other ways you could write it, like 5 times the square root of 3 divided by 5, but that's not meaningfully different. Okay, we need to include the square root. But it's over root 4, and root 4 is 2, so we can simplify that a bit. Now, you know, I want to really slow things down here because trigonometric equations, and I know this from the last unit exam, and I know this from experience, are challenging for students. So again, I want to remind you that there's two general schools of thought here with how we proceed. One is you go to your unit circle. And the only reason why you can go to the unit circle, everybody, is because you would recognize root 3 over 2 as being a coordinate on the unit circle. I suppose if you don't recognize root 3 over 2 as being a coordinate on the unit circle, then it's not going to occur to you to go to the unit circle and you'll take the other path. Okay? But on the unit circle, root 3 over 2 is a coordinate. So I'm just going to sketch a little unit circle here. And I'm going to say that since it's cosine, it's the x coordinate on the unit circle. I'm really pooling together a whole bunch of pieces of knowledge that I have about trigonometry and proceeding here. It's the x coordinate on the unit circle. And from experience or from memory, I know that the root 3 over 2 happens with the 1/2. There are points on the unit circle that have an x or a y coordinate of root 3 over 2 and a y or an x coordinate of 1/2, positive or negative. So if I know that it's the x coordinate that's going to be root 3 over 2, plus or minus, then I know that the y coordinate is going to be the 1/2. And that tells me that, I'm going to actually break this down. I'm going to write cosine of x equals root 3 over 2, and cosine of x equals negative root 3 over 2. So where is cosine root 3 over 2? It's root 3 over 2 here and here at these two places. And again, this is a unit circle approach. If this is a written response question, you would actually write in the coordinates. And I'm going to do so. I'm just going to have to make this a little bit smaller. My planning here on my space wasn't very good, but I'll just make this a little bit smaller. This would be a coordinate pair of root 3 over 2 comma a half. This would be a coordinate pair of root 3 over 2 comma negative a half. But those two locations satisfy the first equation. And again, everybody, I'm reviewing right now unit 3. This is not anything new. These 2 points correspond to positions that make that equation true. On the other hand, where is cosine of a rotation angle negative root 3 over 2? Well, that would be here and here. These two places have x coordinates of negative root 3 over 2. So this is negative root 3 over 2 comma 1/2. And this is negative root 3 over 2 comma negative 1/2. So this second half of the equation, and it's what, quite frankly, many of you, this question might have even been on your exam. Many of you missed the plus or minus. So you just picked those 2 points. Those are the 2 positions for the second equation. So again, this is just a unit circle approach. That means that this is going to get pretty ugly. This is an angle. This is an angle. This is an angle. And that is an angle. All 4 of those are angles. And we're asked to go from 0 to 360. So it's going to be 30 degrees to the first, 150 to the second, 210, and then 330. And I'm just going to pause there. This is 30 degrees. This is 330 degrees. This is the 150 and the 210. So I'm just going to pause there just to make sure that everybody understands those 4 highlighted points. Don't worry about all the swirls and lines. Those 4 highlighted points can be described by those 4 angles I've written down. Are you okay with that? Ian? When you're asked to solve an equation, you're asked to find the value of the variable in the equation. Since the variable is x and x is an angle, you're asked to find the degrees. You would never be given an equation that's trigonometric where it says solve and you're trying to find the locations or the coordinates. We want to describe our solutions as rotation angles, not positions. We use, this is a good conversation we're having, we use those positions to determine the solutions. But I really like this question. Our solutions are what I have written down here in the bottom right corner of the screen. This diagram is not showing the solutions. It's showing positions that we can use to find the solutions. Well, I guess these curves, these arcs I've drawn, are indicating the solutions. Okay? So that's if you're a unit circle kind of person. Now, you don't have to be a unit circle kind of person. And again, I don't believe this lesson today is very long, so I want to make sure that we get off on the right foot here. If you are a reference angle kind of person, then you still have that same work to do to get you here, right? You have to do the algebra to get you here. And then you say, well, what is the reference angle? Well, the reference angle, you go to your calculator, and you're going to put your calculator in degrees. And I'd like you to follow this, just humor me. Follow along on your calculator. You put your calculator in degrees. Listen carefully. Not because we want an answer in degrees, but because even if we wanted an answer in radians, you want to recognize the angles. And we only recognize degrees, at least I do. So the reference angle will be the inverse cos, this is how we write it, of root 3 over 2. Over here, the reference angle will be the inverse cos of root 3 over 2. Because we don't include the negative. And my point is, you're going to get the same reference angle for both, right? So when you go inverse cos in degree mode of root 3 divided by 2, I sure hope you get 30 degrees. Okay, so you get 30 degrees for a reference angle for both of these. Now, with the equation on the left, cosine is positive, and cosine is positive in quadrant 1 and quadrant 4. So you draw a reference angle of 30 degrees there, a reference angle of 30 degrees here, and I hope everybody sees how that is going to give us 30 degrees and 330 degrees. Yes? The rotation angles will be this one and this one. So there will be your 2 of the 4 solutions. If, on the other hand, cosine is negative, which it is in this equation, then it's going to be in quadrant 3 and quadrant 2. So this is 30 degrees, this is 30 degrees. The rotation angles will be 150 and 210. So that's how you would solve it algebraically. Okay. Let's solve this equation now graphically. And you don't really have to show any work here. When you solve something graphically on an exam, it would only ever be for a multiple choice or a numerical response question. There is literally no work to show. So what I'm going to do is, well, I'll write this out. If we have 4 cos squared x minus 3 equals 0, then I can change this to y equals 4 cos squared x minus 3 and find the x-intercepts of the graph. It's not what I would do. I'll show you what I would prefer to do in a second. So following along on your calculator, we're going to enter 4 times cosine of x quantity squared. I've talked about this before. That's how you enter it. It looks like maybe you're taking the cosine of x squared, but you're not. You're squaring cos of x. If it was only the x being squared, I'd have to put that squared inside of the brackets. And then minus 3. I'm going to make sure I'm in degree mode. and I'm going to go zoom standard. Sorry, I'm going to go zoom trig. Because zoom trig goes from negative 360 to 360, and I'm interested in 0 to 360. So I'm only interested in solutions from 0 degrees to 360 degrees. And 360 degrees is about there, and 0 degrees is there. So first of all, this is very interesting, because if I give you this question as a multiple choice question on an exam, if you graph that function, you can immediately see that there are 1, 2, 3, 4 answers. And like I said, I think this question might have actually been on your exam, and 2 of the choices only had 2 answers. If we find those x-intercepts, and I'm not going to find all 4. Okay, we go to our calculate menu and we choose 0, and we put the cursor to the left of an x-intercept. I'm going to go with the first one. We hit enter. We scroll because it's saying right boundary. We hit enter, and you're going to get 30 degrees. And you could find the other ones that way as well. One final observation here. If you take this equation and move the 3 over, this is how I would actually prefer to solve this graphically. I would graph y1 equals 4 cos squared x, y2 equals 3, and I would not worry about x-intercept. I'd look at where they cross, where they intersect. And I don't know, let me walk you through this process and ask your opinion on something. So 4 cos of x quantity squared, and then 3. So I'm looking now at not the x-intercepts, but I'm looking at where these graphs intersect. So I'm going to pick on the first point of intersection. Which would be this point here. I go to my calculate menu and choose intersect. My question to you is, I want your opinion on this. Doesn't it seem easier to just scroll close to that and hit enter 3 times? Rather than having to worry about to the left and to the right. To me, this is just simpler. If all I have are 2 functions, and I choose intersect, I just have to go first curve, second curve. The calculator does all the work for me. I don't have to scroll around. I just have to scroll to close to the x-intercept. Sorry, close to the intersection point, not x-intercept. Okay, any questions with example 1? So I want to summarize example 1 by saying with this particular question, you could solve it algebraically or graphically. Now when we take a look at example 2, you cannot solve this algebraically. I want to repeat that. You do not know how to solve this algebraically. And the reason is, it's not sine of x, it's sine of something more complicated. Than x. If you try to rearrange this equation and then take the inverse sign to find a reference angle, you will be finding a reference angle not for x, you will be finding a reference angle for 2x minus 7. What does that even mean? I can't wrap my head around that. And for that reason, with this type of equation, you must solve this graphically. By the way, let's just stop for a second. You might notice that I had 4 questions here. This was a question on your exam. Now, your exam might have said -4/7, or it might have said -4/9. But let's say I wanted to solve this. Am I right in saying that on your exam it went to 4 pi? Okay. If I wanted to solve this, and Ian, you and I did this on paper yesterday, right? We found a reference angle. We had to take 4 pi minus the reference angle. It was quite a process. But if I wanted to solve this and I want an answer in radians, so I could put my calculator in radians, I guess what I could do is the following. I could graph tan of x, and I could graph -4/7, and I could find out where they intersect. Right? And I want to go from 0 to 4 pi. Well, why don't I just go to my window setting right now and change this from 0 to 4 pi? Everything else really doesn't matter. When I graph it, here comes the tangent function, which you should be familiar with from yesterday. Here comes -4/7. All of these points now I think this one, whoops, all of these 4 points where the line -4/7 intersects with tangent of x are solutions. So what's the biggest one? This one. If you find the x coordinate of that point, that's the answer. There were at least 4 or 5 questions on the exam that you could have solved graphically. Now, don't be angry with me and say, well, how come you didn't tell us this before we wrote the exam? Because I know if I do, nobody learns how to do it algebraically, and you have to do it algebraically. You have to know how. We could solve this one graphically. We could solve this one graphically. You could solve this one graphically. You could solve any of these graphically, but you never know which one would be asked as a written response where you can't. Now, getting back to example 2, you cannot solve this one algebraically. So we're going to solve it graphically, but it's very important that you pay attention to 2 points I want to make before we even put it into the calculator. In order for this to work, you need to know the period and you need to know the range. If you don't know the period of the trigonometric function and you don't know the range of the trigonometric function, it will not work. So when I take a look, I'm going to get rid of this. When I take a look at this being, say, y2 and this being y1, and I talk about this right-hand side being a trigonometric function, what is the period of that trigonometric function? We have to go back to the previous unit to figure that out. I would like everybody to figure out what the period of that trigonometric function is. By the way, there's no degree symbol here, so we have to work in radians. Jonathan, do you know? It's not 2. It's related to the 2. B has a value of 2. Arissa, do you remember? It's pi. Because the period of a sine or a cosine function is always 2 pi over b. And b is 2, so 2 pi over 2 is pi. Okay. We'll find the range now, but then I'm going to explain why this is important. So what is the range? Well, this graph has a vertical displacement of 8. That means that the middle of the graph is going to be at y = 8, and this graph has an amplitude of 6. So 8, this is d, that's the vertical displacement. This is a, which is going to lead us to the amplitude, which is 6. And that means that the graph will go 6 above 8 and 6 below 8. It's very important that you find the period and the range here. So 6 below 8 would be at y equals 2. 6 above would be y equals 14. So the range is from 2 to 14. Why are we doing this? Well, we're doing it because zoom trig is not going to work all the time here. Zoom trig is not going to work because we're taking the sign of not x, it's the sign of something else. And sometimes these numbers get so big in the hundreds that zoom trig is just it's a lost cause. We are doing this to lead us to the window settings. If we don't know the period and the range, we can't enter appropriate window settings. If the range is from 2 to 14, then our window settings have to go from 2 to 14. At least. I would probably go from 0 to 14 or 0 to 16. And the general rule, everybody, is we always want to look at one period horizontally. So we're going to go from 0 to pi. Always want to go for one period, not 2 pi, not 8 pi, one period, which in this case is pi. And the range is 2 to 14. So in my window settings, I haven't even entered the function yet. In my window settings, I'm in radians because I don't see a degree symbol. In my window settings, I'm going to go 0 to pi. The scale you use is absolutely unimportant. We could go up by pi over 6. I don't care. You know, if I enter pi divided by 6 here, it just means I'm going to see a tick every pi divided by 6. It's not important. And I said we have to include 2 to 14. I'm going to go 0 to 16 with a tick every 2. And we enter the function. Well, we enter both functions, right? We have to enter y equals 10. And we have to enter y equals 6 sine brackets 2x minus 7 n bracket plus 8. I want to review some things right now with you. You have to find the period and the range to set up the window settings so that you will see a full cycle of the graph, always. You have to be in radians because there's no degree symbol. Graph. Now, oh, there it is. There's the 10 and there's the other one. So I'm seeing that this thing has two solutions from 0 to pi. Let's find those numbers. So let's find the decimal values here of those 2 points of intersection. So calculate, intersect. Well, I'm close to this one right now. I'll just go enter, enter, enter. So one of the solutions is 1.76 approximately. The other solution, I'm going to repeat the process. This time I'm going to go closer to the other one. Enter, enter, enter. And I get the other solution. So, those two numbers are solutions to this equation. Now let's look at, just hang on to your question for a second, Ian. Let's look now at what the question says. It says over all real numbers. Okay? So let's talk about this solution here. This has a solution of 0.528328 because it's where that periodic graph is intersecting the line y equals 10. But if this graph, everybody, is periodic, make it a little bit smaller. If this graph is periodic, then it repeats. And this is one of the reasons why we only were interested in graphing one period. This is going to repeat. It's going to keep intersecting at that part of the curve over and over and over again. Well, what is the distance from here to here? What is that? Well, that's pi, because the period is pi. Which means the solutions from 0 to pi would be x equals 0.53 and x equals 1.76, but the solution over all real numbers would be that. So what you're doing with these equations that need to be solved graphically is you're finding the solutions in one period, and then you're adding multiples of the period to get the rest of the solutions. If it says over all real numbers, and it may not. Ian.
I was just wondering why we were only looking at the first set instead of all of them, because I thought there was a range in the question that I didn't see, but that we solved for.
And I want to, so your question's been answered, but I want to correct one little thing you said. You were looking for a range in the question you didn't see. What you were looking for was a domain in the question you didn't see. And I'm just being, I know you're using the word range as the English language understanding, but yes, you're right. Any questions with that example? The biggest thing is this mess that you're taking the sign of is not just x. You can never, there'll be an exception to this at the end of this unit. You can never algebraically solve a trigonometric equation if the argument of the trigonometric expression is bigger than x. If it's x plus 8, forget about it. If it's 5x, don't do it. Solve them graphically. Okay, let's try another one. So now we're going to look at some applications. There are these things in nature called tides. They happen because of the gravitational pull of the moon on the oceans. And throughout the day, what happens is the water level or depth in a harbor will go up and down and up and down, and it will do that over and over again. And this is giving you a function that says d is the depth of water in meters and t is the time in hours after midnight for a particular depth of water in a particular harbor. Now, this says d of t. We've talked about this many times before. If you were confused by the function notation, then forget about it. It's not really that important in the context of this question. D as a function of t simply means the depth of the water depends on the time. It's identifying for you, and those of you in calculus will appreciate this more, it's identifying for you that t is the independent variable. So if you were to differentiate, you'd be finding dd dt. And if you're not in calculus, I just spoke gibberish to you, okay? That's the time. So we want to find d here. This we can actually just put into our calculator without a graph, but I am still going to solve this graphically. So this will be 2.83 repeating plus 18.5. Well, we'll solve it on our home screen of our calculator first. Then I'll show you that we could have solved it graphically as well. But I feel really bad for that. That's a horrible blunder. That is a time, not a distance, not a displacement, not a depth. So we want to be in radian mode. I think I still am in radian mode, obviously. I say obviously because there's no degree symbol. That's why we want to be in radians. So I can just go to my home screen and enter -8 cos pi divided by 6 times 2.8 with a whole bunch of 3's close the brackets on that and go plus 18.5. Just double check my entry. I think it looks good. Can you let me know if you were also getting 17.8 meters? Okay. So the answer to A is the depth is 17.8 meters. Okay. Because of my blunder, I just want to pause there. Are we okay with A? Okay. When we take a look at B, B is given a depth of 25 meters, which means you have to solve this equation. So now we're solving for t. You cannot solve this algebraically. So we need to know the period and the range of this function to solve it graphically. The middle of this graph is at 18.5 meters. The amplitude is 8. So we can figure out from that what the range is going to be. It's from 8 below 18.5 to 8 above 18.5. It's from 10.5 to 26.5. How is my addition and subtraction? Good. So that's the range. The period is 2 pi over b, which is 2 pi over 6. I'm going to multiply top and bottom of this fraction by 6. What happens is the 6's cancel, the pi's cancel, and I'm left with a period of 12 hours, which totally makes sense because tides go in and out every 12 hours. You may not know that, but that's a fact. That's what tides do. Okay. So the period is 12 hours. The range is 10.5 to 26.5. So when I set this up in my window setting menu, I'm going to go from 0 to 12. My recommendation is go exactly one period. Don't go a little bit before and a little bit after. It could cause problems. And for my Y min, I'll go 8 to 30. I do like to have a little bit of cushion here between the lowest and the highest, or above the highest and below the lowest. And now I can enter my equation that I'm trying to solve. We're looking at what I have written in B. So we want 25 to be the same as negative 8 cos pi x over 6. This is just how I prefer to enter pi over 6 times x. Because if I enter pi over 6 times x, it almost looks like it's pi over 6x. It's not, but it looks weird to me. So that's why I prefer to do pi x over 6. And then I have plus 18.5. Double check a few things. Did I enter the equation correctly? Yes. Am I in radians? Yeah. My window setting appropriate? 1 period and up to the maximum of, I don't know why I went to 30. Oh, right. It went up to 26.5? Yeah. So I should see my horizontal line, and then I should see the wave. So you'll notice there are two solutions here. There's a solution here and here, but the question is, when does the water first reach a depth of 25? So all we need to do is find the x-coordinate of that first intersection point, and we will have our answer. And this is why I prefer the intersection method as opposed to the x-intercept method as well. With a problem like this, you'd have to zero the equation and find x-intercepts. It's more work. So the answer to the question is 4.8 hours after midnight. I don't think you would ever be expected to convert that to hours and minutes. So we just say 4.8 hours after midnight. All right. Any questions with B? All right, C says, what percentage of the time is the depth of the water greater than 20 meters? Well, let's put 20 in instead of 25 and take a look at the graph. So at some point in time, the water is rising and it reaches 20 meters. The water continues to rise above 20 meters, and then it reaches its peak, and then it starts to drop because the tide is going out. And it reaches 20 again, and then it goes below 20. So this is the part of the cycle that's above 20. We have to start by finding out how long it's above 20, which means that you need to calculate this time and this time so we can figure out how many hours it's above 20. And that means you're going to find both t-intercepts or x-intercepts. So you go ahead and do that. I'm going to do the same thing up here. So it's about 3.36 hours to 8.64 hours. Can you confirm the same numbers? Okay. So how long, how many hours is the water above that? Well, we can subtract those two to get a difference of 5.28. Thank you. 5.28 hours. Now, there are two questions that are frequently asked on exams, diploma exams and my exams. For how many hours is the depth above 20? And the answer would be 5.28 hours. The more complicated one is what percentage of the time is it above the 20 meters? How can we figure out what percentage of the time this 5.28 hours is? Why 12? Right, that's the period. That's the whole time here. This is 12 hours. So looking at it, I mean, if I gave you an exam with 12 marks and for some reason I gave you 5.28 marks out of the 12, your percentage would be 5.28 divided by 12 times 100, which is going to be a little less than 50%. We've been around long enough in high school math to know that if this were a numerical response question, you would want to be careful to carry a significant number of digits. You know, don't do any wild rounding partway through your work. So it's actually 5.2795 divided by 12 and then times 100. Gives you about 44% of the time. So the answer to part C is 44%. Any questions with C? Yeah.
Could you go back, Rush,
Certainly.
Thank you.
You're welcome. I did mention that after my blunder with A that Jonathan corrected me for, and I appreciate that, I said you could have still done A graphically. And let me show you what that would look like. There's a whole slew of ways you could do it. I hope you recall that how I answered A was I typed that whole thing into the home screen. What I could have done instead is just graphed the function. And then there's a couple of things I could have done. I could have hit the trace key and entered 2.833333333 and hit enter, and it will tell me why. Or I could have set up my table to be in ask mode and gone to my table and entered 2.8333333. In other words, everybody, this is a reminder of things that you've probably been told in other courses and this one. You can set your calculator up to accept an X and output a Y, but you can't do it the other way around. If you want to find Y, you're going to have to use a graphical method. All right, let's take a look at the final question. The final question is an application where you're not given the equation of the function. It says a Ferris wheel at Westworld Theme Park has a diameter of 18 meters. It moves in a complete revolution 6 times every minute. And the bottom of the Ferris wheel is 4 meters above the ground. Joel and Ellie start the ride at the bottom. So Joel and Ellie get on the ride, and then they start the ride, and it starts going around and around and around. So here's a diagram of it, and we're asked to determine the equation relating the height of Joel and Ellie above the ground as a function of time in seconds. So what I've done is I've added a graph to the right of it, and that's what you should do. What we can do is put an x-axis that is level with the ground so that our graph is going to be showing height above the ground. In other words, by setting up a graph this way, this value becomes 0. Right? And that's 0 meters above the ground. This will be our time, and this will be 0 seconds. So this graph is going to be showing Joel and Ellie's height starting at 0 seconds. Now we know Joel and Ellie start 4 meters above the ground, which means that this y value, or h value if you like, is 4. And we know that that's where they start. And after one complete rotation, they're going to end up back in the same place. So what I'm doing, everybody, is I'm building a visual of one complete cycle of the graph so I can come up with the equation from what I draw. We also know that there's a maximum height. And, you know, it would really make sense, although it's not that helpful, that whatever this time is to here, half of that time will be when they're at the top. Is that line not flat? Guess not. Oh, look at that. We know that halfway between when they're at the bottom and when they return to the bottom, they're going to be at the top. Look, I hope it's obvious, everybody, that when this Ferris wheel turns around, their height is not going to be represented by that graph. This is a circular motion, and just like circular motion with the unit circle, the height is going to trace out a trigonometric function. So this graph is going to, just want to break this in half, although it doesn't really matter. This graph is going to go up and down. And I can do a lot better than that. I'm going to break it up further into 4 chunks, and I'm going to include, I was being a little lazy there, the middle of the graph. This is what we did in the last unit. So it's got to go up, up, down, down. It's got to go up to this point, continue up to this point, down to this point. It's going to look like this. So we need to determine the equation of that graph that we've just drawn. And incidentally, I think some of you would be able to come up with the equation without drawing this. Okay. So let's start with A. What is A? Well, the lowest point of this graph is 4 meters. That's Joel and Ellie's minimum height. The diameter of the wheel is 18 meters, which means 4 plus 18, that's the diameter, has to take you up to 22. I would like everybody to find the middle value of y there. I'm getting 13. By the way, when I found the middle value, I just looked at the fact that if this is 18, then the amplitude has to be 9. Right? This distance here, which we call the amplitude, must be 9. So I just added 9 to 4 to get 13, and then I did a double check and I added 9 to 13 to make sure I got 22. Okay, so A is 9. Now, let's not quibble about that. We may make a correction to that. A is 9, though. Okay. D D is 13, isn't it? Because that's the midline, and D is always the vertical displacement. How are we going to determine B? Well, B will be 2 pi over the period. This is the period here. It's how long it takes for one complete cycle. So I would like everybody to figure out how many seconds it takes for Joel and Ellie to return to the lowest point. I think it's 10, isn't it? I've chosen some numbers that work out nicely because this wheel moves around 6 revs in 1 minute, which is 60 seconds. We are asked to find the equation where time is in seconds, so that's why I changed it from a minute to 60 seconds. If it goes around 6 times in 60 seconds, it goes around once in 10 seconds, which means this K is 10 seconds, so B is 2 pi over 10, or pi over 5. Now, the assignment that's currently due on Thursday, you have to find a value of C, right? And I had a discussion with you yesterday in class about a couple of ways you could do it. And in your assignment, luckily, because you're given the coordinates of the max-min, you can find C by doing an algebraic substitution. And you can go back and watch that video from yesterday if you need to. Do I need to worry about C here? What's the condition? Did it say this had to be a sine function or a cosine function? Did it tell us? Or did it just say find a trigonometric function? Determine the equation relating the height. Well, anybody want to take a stab as to why I'm going to choose cosine instead of sine here?
Because it starts at 4 meters, so it started above 0, and that means that would mean cos would normally start above 0. It wouldn't start directly at the center.
Turns out no. So I just want to adjust something you said there. It isn't that cos starts above 0. Cos starts at the top. Because if this has a vertical displacement upwards, every point is going to be above, whether it's a sine or a cosine. So that's not actually the reason why I want to use cosine. Ian?
So that you can justify adding a c value?
No, and in fact, I'm going to use cosine so that I can do this. Marcel, do you know what I'm thinking here?
Because sine starts at the middle, but the graph doesn't start at the middle, it starts at the bottom, and cosine is just the bottom negative flipped, I guess.
Yeah. So sine, here's the starting point. We may have lost sight here with all the stuff I've drawn on here. This is the y-axis, and this graph starts at the bottom. If it's a sine graph, it starts here going up. Now, I could use sine, but then I would have to add 2.5 seconds to move it over, because that's a quarter of the period. What I'm saying is if we go with cosine, cosine has a start point up here and goes down, and then Marcel is just pointing out, well, why don't we just flip it over? In other words, if I do that, I don't have to worry about c. Now, it may be that on an exam you're asked to find an equation that uses sine or cosine with a positive a. You would then have to work out what a is, or what c is rather. But if it were sine and it started here going up, I hope you see that this distance time-wise would be c, if it were sine. And figuring out what that is pretty easy. As I said, it's a quarter of the period. So what is the equation? The equation is height equals -9 cosine pi over 5 times t, close brackets, plus 13. And if you wanted to, you could put that into your graphing calculator and see that Joel and Ellie will start at 4, and 10 seconds later they will be back at 4, and they will have a maximum of 22. Any questions with that final example? Okay, once again, I apologize for my mixing up the variables in that example. I think it was example 2. Anyway, on page 275, I think it says on your handout 4 and 5, A and C. You can do them all. Or not. You can do A and C if you like. You know what I'm like in this course. You need to practice this. All of these questions on page 275 and 4 and 5 are solving equations graphically. Setting up the window settings, finding the coordinates. And then 7, 10, or 9, 10, and 13 are word problems, where you're given the equation. It's like the tide question. So get to work on those. You have about 15 minutes here in class to work on them, and I will be around to help you out.